Chapter 3. The Three Roles of Lipids. Lipids are usually discussed in fragments. In one context, they are described as fuel. In another, they are described as membrane material. In another, they appear as precursors for hormones, inflammatory mediators, or signaling molecules. Each of those descriptions is true, but the separation has created confusion because it encourages people to think these are different stories rather than different expressions of the same biological reality. The same lipid that becomes part of a membrane can later be mobilized under stress. The same fat that serves as stored energy can alter signaling indirectly by changing insulin dynamics, mitochondrial load, or substrate competition. The same fatty acid incorporated into phospholipids can later be released and converted into eicosanoids, resolvins, protectins, or other signaling molecules that change immune behavior, vascular tone, and tissue repair. Lipids do not live in one category at a time. They move between structural, energetic, and signaling roles depending on tissue state, metabolic context, and the needs of the organism. That is why they sit so close to the center of physiology. They are not one nutrient class among many. They are one of the body's major multi-role material systems. The first role of lipids is structural, and this is the most foundational because it sits underneath the other two. Lipids build membranes. They create the boundary conditions required for compartmentalization, gradient control, receptor function, vesicle trafficking, barrier integrity, organelle identity, and cellular decision-making. Without lipid structure, there's no meaningful inside and outside, no mitochondrial membrane capable of oxidative phosphorylation, no synaptic membrane capable of rapid neurotransmission, and no epithelial surface capable of regulating absorption without losing barrier control. Structural lipids do not merely hold the body together in the crude mechanical sense. They create the surfaces through which biological order is maintained. Their saturation level, fatty acid composition, cholesterol interaction, oxidative stability, and distribution within phospholipids all change how the membrane behaves. That means structural lipids determine not just what the body is made of, but how its interfaces perform under normal conditions and under stress. The second role of lipids is energetic. This is the role most people know, but is often explained too simplistically. Lipids are energy-dense molecules, and many tissues are adapted to oxidize fatty acids efficiently under the right metabolic conditions. Triglycerides store large amounts of chemical energy in a compact, water-sparing form. During fasting, sustained exercise, carbohydrate restriction, or ordinary background metabolism in certain tissues, fatty acids can be mobilized from adipose tissue, transported into cells, activated, shuttled into mitochondria, and oxidized to generate acetyl-CoA, reducing equivalents, and eventually ATP. That energetic function matters enormously, but even here the structural story remains upstream. Lipids can only serve as efficient fuel if the machinery that processes them is intact. Mitochondria must have functional membranes. Carnitine-dependent transport must work. Electron transport complexes must remain organized. The cell must be able to handle beta-oxidation products without creating excessive oxidative stress or redox imbalance. So even the energetic role of lipids cannot be separated from structure. The body does not simply burn fat. It uses structurally organized systems to convert certain lipids into usable energy under defined physiological conditions. The third role of lipids is signaling, and this is where much of their complexity becomes visible. Lipids are not silent materials. They act as precursors, cofactors, organizers, and direct participants in communication. Membrane-derived fatty acids can be released and converted into eicosanoids, leukotrienes, prostaglandins, thromboxanes, lipoxins, resolvins, protectins, marazins, and many other mediator classes that influence inflammation, vascular behavior, platelet activity, immune recruitment, pain signaling, and tissue resolution. Cholesterol serves as the backbone for steroid hormone synthesis, making lipid biology central to endocrine regulation. Phosphoinositides and related membrane lipids participate directly in intracellular signaling cascades. Diacylglycerol and ceramides influence kinase activity, apoptosis, insulin signaling, and stress responses. Lipid rafts and membrane microdomains help determine which receptors encounter which partners and how strongly downstream pathways are activated. In other words, lipids do not simply carry signals after other systems have spoken. They are part of the language of the body itself. These three roles are not parallel tracks. They constantly overlap. A membrane phospholipid is structural until phospholipase activity releases one of its fatty acids for signaling. A stored triglyceride is energetic until its mobilization changes the hormonal and inflammatory environment of the body. A signaling lipid can alter gene expression and thereby reshape future structural composition. The body is continuously converting lipids from one role into another. That conversion is part of metabolic intelligence. It allows stored matter to become energy during demand, structural material to become inflammatory substrate during threat, and signaling molecules to drive reconstruction after damage. But it also means that lipid imbalance rarely stays confined to one domain. A problem that begins as poor membrane composition can later appear as signaling distortion. A problem that begins as disordered fuel handling can eventually change membrane turnover and inflammatory behavior. A person may think they have separate issues involving energy, inflammation, and tissue fragility, when in fact all three are expressions of disrupted lipid role integration. This integration is especially important in chronic disease. A body built from unstable membrane lipids may interpret signals poorly, leak gradients more readily, and become easier to activate under stress. If that same body also stores and mobilizes fat in a metabolically dysregulated way, energetic instability increases. If the stored and structural lipid pools are also biased toward pro-inflammatory signaling outputs, the organism does not just have an inflammation problem or an energy problem or a structural problem. It has a lipid coordination problem. The three roles are no longer cooperating. Structure becomes fragile, fuel handling becomes inefficient, and signaling becomes distorted. The result is the familiar pattern of chronic modern dysfunction: unstable energy, exaggerated inflammatory behavior, poor recovery, barrier weakness, endocrine inconsistency, vascular stress, neural irritability, and difficulty returning cleanly to baseline once a challenge has passed. This is why any serious discussion of omega-3 must be placed inside all three roles at once. Omega-3 fatty acids are structural because they enter phospholipids and alter membrane composition. They are signaling relevant because EPA and DHA provide substrate for specialized mediator families involved in inflammatory resolution. They are also energetically relevant, though less central in this regard than some other fats, because their presence influences whole system substrate balance, membrane-dependent mitochondrial performance, and the broader metabolic environment in which energy conversion occurs. Yet omega-3 never acts alone. Its effects depend on the surrounding lipid landscape. A membrane already destabilized by oxidative burden may not benefit from additional highly unsaturated material unless protective systems improve at the same time. A body overloaded with competing omega-6 derived signaling may not express the full benefits of omega-3 incorporation until that broader balance changes. A person with poor mitochondrial structure may not experience better energy simply because fatty acid composition shifts. The three roles always remain entangled. The same logic applies to saturated fats, monounsaturated fats, phospholipids, cholesterol, and tissue-specific lipid distributions. Saturated fats tend to support structural stability and lower oxidative fragility, but their effects depend on proportion and context. Monounsaturated fats often provide a useful balance between flexibility and resilience. Cholesterol is not simply a cardiovascular talking point. It is a membrane organizer and hormone precursor. Phospholipids are not merely dietary trivia. They are the architecture of cell surfaces and organelle boundaries. Arachidonic acid is not merely inflammatory. It is a normal signaling substrate whose timing and magnitude matter. DHA is not merely brain food. It is part of the material environment of neural membranes. The mistake is to isolate one lipid and ask whether it is good or bad, as though biology worked by moral categories. The better question is what role that lipid is serving, in what tissue, under what conditions, and how its presence alters the coordination between structure, fuel use, and signaling. Once lipids are understood in these three roles, many confusions in nutrition and medicine begin to clear. Fat is no longer just a calorie category. Inflammation is no longer just a matter of immune molecules floating in blood. Energy is no longer just a question of eating enough or restricting enough. The body starts to look more coherent because lipids are being seen at the level where they actually operate. They build the surfaces. They store and release fuel. They generate and organize signals. When these roles are aligned, the organism gains stability, efficient energy handling, and cleaner control over inflammatory timing and tissue behavior. When they are misaligned, the same organism begins to fragment into the separate disease categories people usually encounter. The categories are real at the clinical level, but underneath them is one recurring problem. The body is trying to govern itself through lipid systems whose structural, energetic, and signaling functions no longer fit together cleanly. The purpose of this chapter is not just to define 3 lipid roles as an academic exercise. It is to establish a framework for the rest of the book. From here forward, whenever a lipid appears in the discussion, the real question will be which role is being emphasized and which other roles are being indirectly altered at the same time. A fatty acid entering a membrane is never only structural. A signaling mediator released during inflammation is never unrelated to the membrane it came from. A fuel substrate entering mitochondria is never separate from the membrane conditions that determine how well that oxidation can proceed. The body uses lipids because lipids can become matter, energy, and instruction without leaving the same biological language. That is their power. It is also why misunderstanding them has produced so much confusion in modern health thinking. Structural lipids. Structural lipids are the lipids the body uses to build itself. That statement sounds simple, but it has consequences that reach through nearly every level of physiology. A structural lipid is not defined by whether it can be burned for energy or turned into a signaling molecule later. It is defined by the fact that it becomes part of the physical architecture of the cell. It enters membranes, contributes to organelle boundaries, affects barrier integrity, shapes the local environment around proteins, and helps determine whether cellular surfaces remain stable, flexible, selective, and responsive under stress. Structural lipids, therefore, do not sit at the edge of biology as passive material. They help create the surfaces through which biology is allowed to happen. When their composition is coherent, cells maintain cleaner signaling, stronger compartment control, better gradient stability, and more reliable tissue behavior. When their composition is poor, function becomes less precise long before obvious structural failure appears. The most important structural lipids in the body are phospholipids, sphingolipids, cholesterol, and the fatty acids esterified into those larger membrane components. Phospholipids form the basic bilayer architecture because their water-attracting head groups and water-avoiding fatty acid tails allow them to self-organize into membranes. That self-assembly gives biology one of its most powerful material tools, a boundary that can hold difference across 2 sides while still allowing regulated exchange. But phospholipids are not all the same. Their head groups differ, their fatty acid chains differ, and the position of those chains within the molecule affects curvature, packing, charge behavior, and local protein interaction. Phosphatidylcholine, phosphatidylethanolamine, phosphatidylserine, phosphatidylinositol, cardiolipin, and other membrane phospholipids each contribute different physical and signaling properties depending on tissue and compartment. The membrane is never just made of generic fat. It is built from specific lipids arranged into specific environments. Cholesterol belongs inside this structural discussion because it is one of the major organizers of membrane behavior. It inserts itself between phospholipids and changes how they pack. In some contexts, it reduces excessive membrane fluidity. In others, it prevents phospholipids from packing too tightly. It stabilizes certain membrane regions, helps form ordered microdomains, changes permeability, and influences the movement and clustering of receptors and other membrane proteins. Cholesterol is often discussed only in relation to blood transport or cardiovascular risk, but inside tissues it plays a more basic role. It is part of the architecture that determines whether a membrane behaves like a reliable control surface or a surface that becomes too disordered, too permeable, or too unstable under pressure. A membrane without sufficient structural organization cannot interpret signals cleanly, and cholesterol is one of the molecules that helps maintain that organization. Sphingolipids add another layer of structure that is often overlooked. They contribute to membrane order, support the formation of microdomains, and are especially important in tissues that require durable signaling surfaces, including neural tissue. Sphingomyelin, glycosphingolipids, and related molecules help create more ordered regions within membranes that can sort proteins, cluster receptors, and alter how signals are initiated and contained. In myelin, these structural lipids become especially important because rapid conduction depends on a stable lipid-rich insulating architecture. In immune and epithelial tissues, they participate in surface identity and signal organization. Like other structural lipids, sphingolipids are not inert building blocks. Their presence changes how the membrane behaves as a living interface. The fatty acid composition attached to structural lipids matters just as much as the lipid class itself. A phospholipid carrying saturated fatty acids will pack differently from one carrying monounsaturated or polyunsaturated fatty acids. Saturated chains generally produce tighter packing and greater resistance to oxidative disruption. Monounsaturated chains often allow a useful balance between movement and durability. Polyunsaturated chains increase flexibility and can support dynamic membrane behavior, but their multiple double bonds also increase susceptibility to peroxidation. This means structure is never just about having enough membrane material. It is about what kind of membrane material has been built. A cell surface enriched in highly unsaturated lipids may become more flexible and signaling capable, but if the oxidative environment is poor, that same surface may become chemically fragile and easier to damage under inflammatory stress. The structural value of a lipid cannot be separated from the physical demands placed on the tissue receiving it. This is why structural lipids determine so much more than the appearance of a membrane on a diagram. They influence receptor behavior, transporter efficiency, vesicle fusion, membrane curvature, mechanical resilience, permeability, ion leakage, and the ability of the cell to preserve gradients across time. A membrane must be stable enough to resist collapse into indiscriminate mixing, but dynamic enough to allow transport, signaling, and adaptation. Structural lipids create that balance. They decide whether a receptor can cluster correctly, whether a channel sits in the right physical environment, whether an immune synapse forms cleanly, whether mitochondrial membranes hold proton gradients efficiently, and whether barrier tissues can remain selectively permeable rather than diffusely leaky. In this sense, structural lipids are not merely construction material. They are performance material. The importance of structural lipids becomes even clearer when tissues are compared. Neural tissue depends on specialized membrane composition because excitability, synaptic transmission, myelination, and long-range stability all require finely tuned lipid surfaces. Mitochondria depend on structurally specific lipids such as cardiolipin to preserve crystal architecture and maintain respiratory complex organization. The intestinal lining depends on membrane integrity and lipid-supported junctional organization to preserve barrier control while still permitting absorption. Immune cells depend on surface structure to assemble receptors, reorganize their membranes during activation, and later shift into resolution states. Endothelial cells depend on membrane composition to regulate vascular tone, signal perception, and permeability. Each tissue uses structural lipids according to its own demands, but the rule remains the same. What the membrane is made from changes what the tissue can do. Structural lipids also create long memory inside the body. Once incorporated into membranes, they do not behave like fleeting signals that vanish in minutes or hours. They become part of tissue architecture until turnover, damage, remodeling, or replacement changes them. That means diet, endogenous synthesis, stress exposure, oxidative burden, inflammation, and repair capacity all gradually shape structural identity over time. A person is not just eating fat in the short-term metabolic sense. They are contributing to the material pool from which future membranes will be built and rebuilt. This is one reason structural dysfunction often develops slowly. The tissue is being remodeled over months and years, and the consequences appear first as altered behavior before they appear as visible damage. Recovery also follows this slower logic. Rebuilding structural lipid architecture is more like reconstruction than stimulation. It requires time, repeated material input, and a physiological environment that allows new structure to persist. This is also the level at which omega-3 becomes biologically meaningful beyond marketing language. EPA and DHA matter partly because they are structural lipids once incorporated into phospholipids. They change membrane characteristics, alter substrate pools for future signaling, and modify the environment in which receptors, channels, and enzymes operate. But they are only one part of structural lipid biology. Cholesterol, sphingolipids, saturated fatty acids, monounsaturated fatty acids, phospholipid head groups, and tissue-specific remodeling systems all influence the final surface behavior of the membrane. That is why no single lipid should be treated as the whole story. A membrane is a composite structure. Its behavior emerges from the relationships among its parts, not from the presence of one favored nutrient in isolation. Understanding structural lipids correctly changes the entire nutritional and physiological frame. The body is no longer seen as a machine that runs on fuel and occasionally uses fat for secondary tasks. It becomes a built system that must continuously maintain its surfaces. Structural lipids are part of how that maintenance happens. They determine whether boundaries hold, whether signals are interpreted with precision, whether energy-producing compartments remain intact, whether immune behavior stays discriminating, and whether tissues can absorb stress without losing coherence. They do not merely support life from the background. They are part of the material basis of order. Without them, biology does not simply become inefficient. It becomes less able to remain itself. Energetic lipids. Energetic lipids are the lipids the body uses as concentrated fuel, but even that description needs to be tightened because it is often interpreted too casually. The body does not simply burn fat in a generic sense. It stores specific lipid forms, mobilizes them under defined hormonal conditions, transports them through tightly controlled systems, activates them enzymatically, and then channels them into mitochondria or related oxidative pathways where their chemical energy can be extracted in a stepwise manner. This makes energetic lipids more than passive reserves. They are part of a controlled fuel architecture. Their value lies not only in the amount of energy they contain, but in the way they allow the body to store large amounts of usable fuel without carrying it in a hydrated, bulky, chemically disruptive form. Triglycerides solve a physical problem for the organism. They permit dense energy storage that does not destabilize cellular water balance, and that storage gives the body metabolic range across fasting, exercise, illness, overnight repair, and ordinary day-to-day intervals between meals. The major energetic lipids are triglycerides, which consist of 3 fatty acids esterified to a glycerol backbone. In adipose tissue, triglycerides function as the primary long-term energy reserve. In food, triglycerides also serve as a major incoming lipid form that must be digested, absorbed, repackaged, transported, and either oxidized or stored. Their central role in energy biology comes from the fatty acids they carry. These fatty acids contain long hydrocarbon chains rich in reduced carbon-hydrogen bonds, which makes them chemically valuable as oxidative substrate. When the body mobilizes stored triglyceride, lipolysis releases fatty acids that travel through circulation, usually bound to albumin, until they are taken up by tissues capable of using them. Once inside the cell, those fatty acids are activated to acyl-CoA derivatives and for long-chain species, usually transported into mitochondria through the carnitine shuttle. There they undergo beta-oxidation, generating acetyl-CoA, NADH, and FADH2, which feed into the citric acid cycle and electron transport chain. The energy potential fat is therefore real, but it is accessed through layered control rather than through simple combustion. This control matters because energetic lipids are not meant to be burned indiscriminately. Their use depends on metabolic context. In the fed state, especially when insulin is elevated, fat storage is favored and lipolysis is suppressed. In fasting, lower insulin and higher counterregulatory signals such as glucagon, catecholamines, and in some contexts cortisol, increase triglyceride breakdown and fatty acid mobilization. During prolonged low-intensity exercise, fatty acid oxidation contributes substantially to ADP production. During carbohydrate restriction or longer fasting states, hepatic fatty acid oxidation rises and ketogenesis can begin converting acetyl-CoA into ketone bodies that distribute energy more widely, especially to tissues like the brain during adaptation. Energetic lipids are therefore governed by timing, hormonal state, tissue demand, oxygen availability, mitochondrial capacity, and redox handling. The body does not just ask whether fat is available. It asks whether present conditions allow fat to be used efficiently without destabilizing other layers of metabolism. This is one reason the phrase fat burning is often too crude to explain what is actually happening. Oxidizing fatty acids efficiently requires intact cellular machinery. Mitochondria need structurally sound membranes, organized respiratory complexes, adequate oxygen delivery, appropriate cofactor status, and sufficient redox balance to handle electron flow cleanly. If mitochondrial function is impaired, fatty acid delivery alone does not guarantee efficient energy production. In that case, energetic lipids may be abundant while usable energy remains poor. The problem is no longer substrate scarcity. The problem is conversion quality. A person may store fat well, mobilize fat poorly, transport fat adequately, but oxidize it inefficiently, or generate excessive incomplete oxidation products when mitochondrial throughput cannot keep pace. This makes energetic lipids inseparable from the structural theme established earlier in the book. Fuel only matters if the machine using the fuel retains the architecture required to process it. Energetic lipids also influence stability in ways that glucose-based discussions often obscure. Fatty acid oxidation generally supports slower, steadier ADP production than rapid glycolytic flux, especially in tissues designed for sustained oxidative work. Cardiac muscle, resting skeletal muscle, and liver rely heavily on lipid oxidation under many normal conditions because fat provides a large and durable energy stream. This can create metabolic steadiness when mitochondrial function, oxygen delivery, and hormonal coordination are intact. But energetic stability is never just a property of the fuel itself. It depends on whether fatty acid mobilization is proportionate, whether insulin and glucagon timing remain coherent, whether the person can transition between substrates without excessive friction, and whether tissues are receiving a lipid supply they can actually oxidize instead of merely store. Fat is often described as a stable fuel, and it can be, but only inside a system built to access it properly. The energetic role of lipids also intersects with stress physiology. During acute stress, catecholamines increase lipolysis, releasing fatty acids into circulation to provide fuel for tissues facing higher demand. During prolonged stress, however, energetic lipid use can become distorted. Excessive fatty acid flux into tissues that cannot oxidize efficiently may increase lipid intermediates, redox strain, and inflammatory stress. The same substrate that supports resilience in one metabolic context can contribute to dysfunction in another if flux exceeds processing capacity. This is one reason lipid metabolism cannot be reduced to simple praise of fat oxidation. The question is not only whether the body can mobilize fat, but whether it can match mobilization to oxidation without creating spillover, incomplete combustion, or signaling disruption. Energetic lipids support the organism when fuel release, transport, mitochondrial handling, and tissue demand remain coordinated. They become destabilizing when those layers separate. This coordination is especially important in the liver, which acts as a major traffic hub for energetic lipid handling. The liver takes up fatty acids, oxidizes them, re-esterifies them, packages them into lipoproteins, and under certain conditions converts part of their acetyl-CoA load into ketone bodies. When hepatic handling remains coherent, lipids can be directed toward energy production or export according to need. When it becomes overloaded, especially in the presence of excessive nutrient flux, insulin dysregulation, mitochondrial strain, or chronic inflammatory stress, the liver may accumulate triglycerides and lose the clean balance between oxidation, storage, and export. This is not simply a problem of too much fat. It is a problem of energetic lipid traffic losing control. Storage begins to outpace use, or delivery begins to outpace processing, and the liver shifts from being an adaptive fuel coordinator to being a bottleneck. Energetic lipids also differ from structural lipids in their time behavior. Structural lipids become part of tissue architecture and influence performance over longer remodeling windows. Energetic lipids are more immediately mobilizable. They exist partly to be called upon during need. Yet even here the distinction is not absolute. A triglyceride reserve can alter systemic signaling through adipokines, lipolytic flux, and substrate competition. A fatty acid released for fuel can later influence inflammatory pathways or membrane remodeling indirectly. A tissue chronically exposed to high energetic lipid turnover may gradually change its structure in response. The body does not maintain a perfect wall between lipid roles. It maintains shifting priority. Energetic lipids are the lipid pool most immediately available for oxidation, but they remain connected to the signaling and structural consequences of how they are stored and used. This is where common misunderstandings about dietary fat and metabolic health usually begin. People often assume that consuming fat directly means becoming better at using fat. That is not automatically true. Efficient use of energetic lipids depends on digestive capacity, bile flow, lipase activity, intestinal absorption, chylomicron transport, lipoprotein handling, mitochondrial density, carnitine availability, redox balance, endocrine context, and tissue-level oxidative demand. A person can eat more fat and still fail to oxidize it well if the system required to handle is underbuilt or metabolically inflexible. On the other side, a person with good mitochondrial function and well-regulated lipid metabolism may derive remarkable stability from energetic lipids because the system can mobilize, transport, and oxidize them with relatively low volatility. The difference is not ideological, it is architectural. Seen clearly, energetic lipids are not just calories stored in fat tissue or calories consumed in food. They are part of the body's time management system for energy. They allow energy collected during abundance to remain available during scarcity. They allow tissues to perform long-duration work without constant dependence on immediate carbohydrate intake. They support fasting survival, nighttime metabolism, physical endurance, and background cellular maintenance. But their usefulness always depends on structural integrity and signaling coordination. The body has to know when to release them, where to send them, how quickly to oxidize them, and when to stop. That is why energetic lipids cannot be understood in isolation from membranes, hormones, and mitochondrial architecture. They are the fuel role of lipid biology, but they are still being governed by the same larger principle running through this book. Biological performance emerges from organized structure, and even fuel only becomes useful when the system using it is built well enough to stay in control. Signaling lipids. Signaling lipids are the lipids that carry instruction, timing, and state information inside the body. They do not just sit in tissues as structural matter, and they do not just wait to be oxidized as fuel. They participate directly in communication. Some act as precursors that are released from membranes and rapidly converted into local mediators. Some function as membrane-organizing lipids that change which receptors can interact and how strongly signals are amplified. Some serve as intracellular second messengers that alter kinase activity, calcium handling, gene transcription, vesicle movement, apoptosis, or metabolic direction. Others provide the molecular backbone for steroid hormones that coordinate physiology across entire organs and tissues. When signaling lipids are understood properly, it becomes obvious that lipids are not just supporting communication from the edges. They are part of the language the body uses to decide what state it is in and what state it should enter next. One of the clearest examples is the release of fatty acids from membrane phospholipids during stress, injury, immune activation, or normal signaling events. A membrane is not just a surface, it is also a stored signaling reservoir. Phospholipase enzymes can liberate arachidonic acid, EPA, DHA, and other fatty acids from phospholipid positions, and once released, those substrates enter enzymatic pathways that generate prostaglandins, thromboxanes, leukotrienes, lipoxins, resolvins, protectins, marazins, and related mediators. These molecules do not merely announce that something has happened. They shape the character of the response. They influence vascular tone, platelet behavior, immune cell recruitment, pain sensitivity, fever generation, vascular permeability, phagocytosis, debris clearance, tissue repair, and the active termination of inflammation. That means the signaling output of the body is partly determined by what has already been built into its membranes. The body does not invent inflammatory language at the moment of crisis. It draws from stored lipid material and converts that material into instruction. This gives signaling lipids a distinctive kind of biological power. A protein signal often depends on prior gene expression, translation, folding, trafficking, and release. Lipid signaling can move faster because much of the substrate is already present in the membrane, waiting to be mobilized. The membrane therefore functions as a preloaded signaling platform. Once a trigger reaches threshold, the cell can rapidly generate potent local messages without first synthesizing every component from scratch. That speed is useful in immunity, hemostasis, tissue injury, and many forms of stress adaptation, but it also creates risk. If the stored lipid substrate pool is compositionally biased towards signaling patterns that intensify activation more readily than they support closure, the cell may enter inflammatory states with far greater ease than it exits them. Signaling lipids, therefore, do not just help explain why inflammation happens. They help explain why inflammation takes the specific shape it takes and why that shape may become persistent in some organisms and not in others. Arachidonic acid is central to this discussion because it is one of the major membrane-derived substrates for eicosanoid synthesis. Once released, it can be converted into prostaglandins, thromboxanes, leukotrienes, and other mediator families that influence vasodilation, vasoconstriction, platelet aggregation, vascular leakage, leukocyte trafficking, smooth muscle behavior, pain generation, and multiple layers of immune activation. Arachidonic acid is not inherently pathological. It is a normal and necessary signaling substrate. The problem begins when its mobilization is excessive, poorly contained, or insufficiently followed by resolution chemistry. In that context, the body remains biased toward initiation. The signaling system becomes good at starting defense and poor at finishing it. EPA and DHA matter partly because they change this signaling terrain. They can compete for enzymatic access, alter mediator output, and provide substrate for specialized pro-resolving mediators that help terminate inflammatory activity, restore tissue order, and shift the body from escalation toward completion. This is one of the deepest reasons omega-3 belongs in a signaling chapter rather than being confined to a supplement chapter. Signaling lipids are not limited to inflammatory mediators released into the extracellular environment. Many operate inside the membrane itself or on the cytoplasmic side of it as part of intracellular instruction systems. Phosphoinositides help determine membrane identity, vesicle trafficking, cytoskeletal behavior, and signal relay through pathways that influence growth, metabolism, migration, and survival. Diacylglycerol functions as a second messenger that activates protein kinase C and related pathways, altering cell activation states, secretion patterns, proliferation signals, and stress responses. Ceramides participate in stress signaling, apoptosis, insulin signaling interference, membrane domain formation, and inflammatory amplification under certain conditions. Sphingosine 1-phosphate helps regulate vascular integrity, immune cell trafficking, lymphocyte movement, and survival signaling. In each case, the lipid is not just a passive membrane component, it is participating directly in cellular logic. It changes what the cell does next. Cholesterol also belongs here not only because of its membrane organizing role, but because it is the raw material for steroid hormone synthesis. Cortisol, aldosterone, testosterone, estradiol, progesterone, and other steroid hormones all emerge from cholesterol metabolism. That places lipid biology inside endocrine command. Steroid hormones alter metabolism, mineral balance, reproduction, immune tone, circadian timing, tissue growth, stress response, and long-term adaptation. The body therefore uses lipids not only for local signaling events at the membrane surface, but also for long-distance hormonal coordination across the entire organism. A change in lipid handling can alter endocrine capacity. A change in endocrine state can alter lipid storage, membrane remodeling, inflammatory behavior, and energetic flux. These are not separate systems. They are linked through lipid-based signaling architecture. The membrane's physical organization also creates signaling effects before any lipid mediator is enzymatically released. Certain lipids help form ordered microdomains that concentrate or exclude specific receptors and signaling proteins. That means lipid arrangement determines who can talk to whom at the surface. A receptor placed into one membrane neighborhood may activate strongly because the local partners needed for amplification are present. The same receptor in a different lipid neighborhood may remain quiet, terminate quickly, or fail to couple efficiently. This is signaling by architecture. The membrane is not just storing future mediators, it is already shaping current signal quality by controlling protein geography. In that sense, signaling lipids act both chemically and spatially. They generate messages, and they organize the surfaces across which those messages can be interpreted. This dual role helps explain why signaling lipids can produce both adaptation and pathology. Under controlled conditions, they allow fast local coordination, tissue repair, immune defense, vascular responsiveness, endocrine regulation, and organized recovery after stress. Under distorted conditions, they can drive chronic inflammation, pain persistence, thrombosis risk, endothelial dysfunction, metabolic rigidity, immune overactivation, and failure of resolution. The difference is rarely the existence of signaling lipids themselves. The difference is proportion, timing, substrate balance, membrane state, oxidative load, enzymatic control, and whether the organism can transition from activation to completion without getting trapped in the middle. Signaling lipids are powerful because they are embedded in the structure of the body. They are close to the point of action, and they can move the system quickly. That same closeness is why lipid imbalance can have such broad effects. This is also why signaling lipids create memory inside tissues. A membrane enriched over time with certain fatty acid patterns becomes a reservoir for future signaling outcomes. A tissue repeatedly exposed to oxidative stress or inflammatory pressure may shift not only its acute mediator production, but also the composition of the membrane from which later mediators will be drawn. The next response is therefore shaped by the history of previous structure. A cell that has been rebuilt under chronic inflammatory conditions may become easier to activate because its membranes now contain a substrate mix and signaling organization that favor faster escalation. Another cell supported toward better membrane remodeling and better resolution chemistry may begin responding with greater proportionality. The tissue is not merely reacting in the present, it is reacting through stored structural history. Seen clearly, signaling lipids are the reason lipids cannot be reduced to calories or even to membrane material alone. They are part of the body's operational language. They tell blood vessels whether to widen or constrict. They tell platelets whether to aggregate. They tell immune cells whether to recruit, attack, engulf, clear, or stand down. They tell endocrine tissues how to coordinate long-range adaptation. They tell cells internally whether to grow, divide, move, survive, shut down, or repair. Their power comes from their position at the intersection of structure and action. They are generated from built material, and once generated, they change what the system does. That makes them uniquely important. They are not external regulators dropped into biology from above. They are the instructions that emerge from the body's own architecture. Why these roles must stay balanced. The structural, energetic, and signaling roles of lipids cannot be treated as separate categories that can each be optimized independently. They are physically connected inside the same organism, often inside the same molecules, and the body depends on them remaining proportionate to one another. A lipid that stabilizes a membrane today may become signaling substrate tomorrow. A lipid stored for energy may alter signaling tone through its rate of mobilization, its intermediates, or the tissue stress created when its oxidation outpaces mitochondrial control. A signaling lipid released during inflammation may reshape future structure by altering membrane turnover, oxidative load, gene expression, and tissue remodeling. Because of that, lipid balance is not just about having enough of each role present somewhere in the system. It is about keeping the three roles coordinated so that structure supports function, fuel use supports stability, and signaling supports adaptation without dissolving into chronic activation. The structural role must remain primary because it sets the conditions under which the other two roles can operate safely. If membranes are unstable, overly oxidizable, excessively rigid, or compositionally disordered, then the energetic role becomes harder to execute cleanly, and the signaling role becomes harder to control precisely. Receptors misread. Gradients leak. Mitochondria lose efficiency. Barrier tissues become more permissive than they should be. The body can still mobilize fuel and generate signals under those conditions, but the outputs become noisier and more expensive. Energy production creates more strain. Inflammatory activation becomes easier to initiate than to resolve. The organism begins reacting through weakened surfaces. This is one reason a body can appear chemically active, yet physiologically unstable. It has signaling and fuel flux, but the structural platform needed to govern both has degraded. The energetic role must also stay in proportion because lipids used as fuel can support stability or overwhelm it depending on context. A well-regulated lipid fuel system provides continuity across fasting, sustained activity, and the intervals between meals. It reduces the need for constant external intake and supports long-duration energy production in tissues designed for oxidative metabolism. But when lipid mobilization exceeds oxidation capacity, or when fat is stored efficiently but processed poorly, energetic lipids begin to spill into other roles in damaging ways. Incomplete oxidation products accumulate. Lipid intermediates interfere with signaling. The liver becomes overloaded with lipid traffic it cannot direct cleanly. Oxidative stress rises. Membranes may be remodeled under inflammatory pressure rather than under controlled maintenance. The system then stops using fat as a stable reserve and starts experiencing it as metabolic burden. The same lipid pool that should support resilience begins generating distortion because the energetic role has lost coordination with structure and signal timing. The signaling role is the most volatile of the three, which is exactly why it must remain tied to the other two. Signaling lipids move quickly. They can amplify, recruit, constrict, dilate, sensitize, activate, terminate, or resolve within short windows. That speed is useful during injury, infection, stress, and tissue adaptation, but it also means signaling lipids can dominate the system if the structural reservoir and energetic environment are biased in the wrong direction. A membrane built from unstable or heavily pro-inflammatory substrate can produce signaling outputs that favor escalation more than resolution. A body under chronic energetic strain can convert fuel imbalance into inflammatory language through redox stress, lipotoxicity, and altered mediator synthesis. A system that repeatedly activates without structurally rebuilding will slowly turn signaling into its default mode. At that point, the body is no longer using lipid signals as precise instructions. It is living in a state of continuous lipid-derived interpretive pressure. Balance matters because each role protects the others when properly aligned. Structural integrity limits signaling noise. It keeps receptors organized, barriers intact, gradients preserved, and activation thresholds meaningful. Clean, energetic handling reduces unnecessary stress on membranes and decreases the likelihood that stored lipid will become a source of toxic overflow rather than useful ATP. Well-regulated signaling helps the body respond proportionately and then return to baseline, which protects structure from prolonged inflammatory damage and prevents energy systems from remaining trapped in expensive defensive states. When these roles cooperate, the organism gains something more important than isolated biochemical efficiency. It gains coherence. Inputs are interpreted clearly. Fuels are used without destabilizing the tissues using them. Stress responses begin and end on time. Recovery is possible because the body is not consuming its own architecture while trying to defend itself. When these roles fall out of balance, chronic disease becomes much easier to understand. A person may have enough stored fuel, yet feel underpowered because energetic lipids are not being oxidized cleanly. They may have abundant signaling activity, yet poor adaptation because the signals emerging from membranes are biased toward escalation. They may have tissues that are constantly inflamed not because the body lacks defensive ability, but because structural lipids have been remodeled into surfaces that interpret ordinary life as repeated threat. In another case, a person may improve energy transiently through increased fat mobilization, but worsen inflammatory tone because the structural and signaling consequences of that flux were not contained. Or they may consume more omega-3 expecting resolution benefits while ignoring the fact that highly unsaturated structure introduced into an unstable oxidative environment can become fragile before it becomes helpful. These contradictions are not contradictions once the three roles are viewed together. They are what happens when one lipid function is pushed without regard for the others. This is especially important in the context of omega-3 and omega-6 biology. Omega-3 is often discussed as if increasing it is automatically beneficial because of its signaling potential and its role in resolution pathways. That can be true, but only if structural incorporation is supported and oxidative handling is sufficient. Omega-6 is often discussed as if it exists only as a source of inflammatory excess, but some omega-6 derived signaling is normal and necessary when proportional and properly terminated. The real issue is not moral classification of fats. It is the relationship between structural incorporation, mediator production, and metabolic environment. If a tissue contains excessive pro-inflammatory signaling substrate, unstable membranes, poor antioxidant defense, and high energetic strain, then simply adding more of one lipid class does not guarantee balance. The architecture has to be rebuilt in a way that allows all three roles to re-enter coordination. The body is healthiest when lipids remain obedient to hierarchy. First, they must build stable surfaces. Then they must support controlled fuel handling through those surfaces. Then they must generate signals that reflect real needs and resolve once those needs have been met. If signaling outruns structure, the body becomes reactive. If energetic flux outruns structure, the body becomes unstable. If structure is built without sufficient dynamic capacity, the body may become rigid and unresponsive. Real health is not produced by maximizing any one role. It is produced by maintaining proportion among them. That proportion is what allows a membrane to remain both stable and interpretable, a fuel reserve to remain both available and non-toxic, and a signaling system to remain both responsive and finite. This is the deeper lesson of lipid biology. Lipids do not just do three different jobs. They create a three-part system that has to remain coordinated if the organism is to function with precision over time. When that coordination is present, energy becomes steadier, signaling becomes cleaner, immunity becomes more discriminating, and tissues recover with less collateral damage. When that coordination breaks, the body begins to fragment into the familiar modern pattern of fatigue, inflammation, metabolic dysfunction, barrier weakness, vascular instability, neural irritability, and poor recovery. The failure is rarely in one isolated pathway. The failure is in lipid role balance itself.